Welcome to the second half of Calculus 3. Today we will be covering double integrals. Let's get straight to it. Double integrals we're summing two things, right? So if you remembered from your Calculus 1 course, this symbol right here is like an S. S means for sum, right? It looks like an S, it's a sum. It's just a sum. So what does it mean if we're having an integral from a to b of f of x dx? It means you're summing all of the f of x height. So that's f of x height, right? You're summing all of the you would usually see it like this. So you're summing f of x I, and you're saying it's all the way from I to n f of x I times the change in x, or the change in xi, right? It doesn't matter, but you're summing all of the height. So I'm gonna label that, right? That's f of x, and then you're multiplying that by dx. So f of x dx is this really small area right here. It's it's this really small thin slice of area. And as the area gets thinner and thinner, or I should say this is delta x, but as the area gets thinner and thinner, we approach dx. So f of x times dx is the area of the very little slice with height f of x, and dx is the width of the rectangle. So how do we get the area under the entire curve? The area under the entire curve is all of the components, all of the little bits of f of x times dx. That's why we have f of xi. So we have f of x1, x2, x3, x4, x5, right? Right. So we're taking f of x from here, and then we're taking f of x from here, and then we're taking f of x from here, because there's a different height every time, but it can also be a different width. It wouldn't matter, but we're just going to assume for this one, for simplicity of explanation, is the same width. Right, so we're taking f of x from everywhere. We're multiplying by a small change in dx. So we're getting the area of very small slices. And as you get closer, and as dx gets closer and closer to 0, which means as the width gets closer and closer to 0, we get more accurate slices, or we add up more slices and we get more accurate slices, and that's why we have this notation right here. It's the limit, or I'm sorry, this is equal to the limit as the number of slices n approach infinity. So if there's infinite slices and all the slices are like really, really small, zero small, infinitesimally small, what we will end up with is the area under the curve, the exact area under the curve. So in 3D, we have new notation. It's a double integral this time. Why is it a double integral? Well, I'll explain to you why it's a double integral later. It has something to do with area. Area has 2 dimensions, so we need 2 integrals for 2 dimensions. So the double integral in the region R, so it's not a to b anymore. It can be soon. Soon it will be a to b, or whatever it is, but it's not that right now. So when we put an R down there, it's just the region R. Now I will use R sometimes. I will use D sometimes. R is usually used for rectangles. D sometimes is used for different surfaces, and sometimes different letters are used. Sometimes S is used, for example, especially once we get to chapter 16. Or no, not chapter 16, chapter 5. Chapter 6, I don't even know what chapter anymore. I not really thought about this very, very clearly. Okay. F of xy times dA. What's dA? dA is a small change in area. Or, well, it's not really even a small change in area. It's the fact that A is equal to, or the volume volume is equal to height times base. Base, and the base is the base area, right? So like if we have a, let's just say a rectangular prism. So what's the area of this? It's the base area times the height, or in this case it would be the width. If it was standing up, it would be the height. So it's the area of this thing times however long it is, however long it's projected. So it's the same thing for this one. We're having little cuboids, little rectangular prisms, like small rectangular prisms. And when we add all of those rectangular prisms up, we will end up with the volume. We will add, if we add all of the small rectangular prisms up, we will end up with the volume. So what this is saying is the double integral in the region R, double because there's 2 dimensions, of f of x, y, the height of the function, times dA, the base area of each small piece, will give you the exact area, the exact volume under the surface f of x, y. So let's try to do some of these problems out. Find the double integral of the region R of 3dA, or double integral in the region R of 3dA if the region R is x, y, or if the region R is, this is set builder notation, x squared plus y squared is less than 9. So let's draw a picture. Let's see if we can figure it out. So what is 3? 3 might just seem like a random number, but 3 is f of x, y, right? And when we do interpretations of this in a graph, what we want is we want to set z, the dependent variable, to be equal to f of x, y. So if z is equal to 3, then what we end up with is we just end up with this. We end up with a plane z equals 3. And if we have a region x squared plus y squared is less than 9, that's just a circle with the radius 3. So if we project this up a little bit, this is the volume under the surface right here. And you can realize that this is just a cylinder. Not like the cylinders that we talk about in 1.6. It's an actual just a circular cylinder. A cylinder with a circle on top and on the bottom. So what's the volume of this? Well, it's the area of the circle times the height. So what's the height? The height's 3. We already established that, right? It's 3dA. And then what's the volume of, or what's the area of the circle? The radius is 3, so it's pi r squared. So it's 3 times pi 3 squared. And that's 27 pi. Very simple. These are very simple questions. This one might be a little bit tougher, but still, it can be very simple if you make it simple. So what is the double integral of in the region R of 1 minus 2y dA? So, well, let's draw the pictures. You're not going to be able to draw the picture every single time you do these problems, but when you can draw the picture, you should draw the picture. In fact, the way that we're actually going to be doing these integrals, it's probably better for 1 minus 2y to be done manually rather than done conceptually. This question was done conceptually. You should do this manually using the method that we're going to do later, but I'm just going to do this conceptually with you guys right now. So what does 1 minus 2y look like? 1 minus 2y is independent of x. Right, so x can be absolutely anything. So we have x right here, y, z. X can be absolutely anything, and y would still, and wouldn't affect the graph. Right, so this is basically just z equals 1 minus 2y. because f of xy is equal to 1 minus 2y. So we can actually just draw that on the graph. So what would that look like? That would look like, well, we have a negative 2, or the y-intercept is 1, or the z-intercept is 1. I'm sorry, not the y-intercept, right? And then we'd have something like this, and then this will be your line, right? And since it's a cylinder, since it well, this is basically a plane because it's linear, but I'm calling it a cylinder because it has 2 variables only. It doesn't have a third variable, so it doesn't depend on x. So what we end up with is we get a plane like this. And I'm saying that we could do this conceptually. How can we do this conceptually? Well, let's see. So we notice that this is right here. Just this slice alone, this rectangle right here is above the x-axis. Or not rectangle, I'm sorry. Triangle is above the x-axis. It has a base of 0.5. How would you know that? Well, 1 minus 2y is 0. So y is 0.5. And a height of 1. How would I know that? I plug in y equals 0. I get a height of 1. This also has a base of 0.5. And it also has a height of 1. How would I know that? I would put y equals 1 in there. I would get negative 1. Right? So negative 1 is 1 away from 0. And it's both a positive area and then a negative area. Positive area, negative area. And they're the same area. So if there's a positive area and a negative area and they're the same area, they cancel out. So this should be 0. We'll work it out later. I did not put this in the remainder of the lesson, but I will actually go ahead and do that right now. And we'll see if I'm wrong later on. All right. So this is 0. It doesn't matter what x is. We're just going to get a solid that's sort of like this. Sort of like this. And then sort of like this. Where it's just one rectangular prism right here above the xy plane, and then one triangular prism down here below the xy plane. They have the exact same volume, so the volume is just 0. It doesn't matter what the x difference is. Doesn't matter how much x you're putting, because it doesn't depend on x. How much x there is, because it doesn't depend on x. Okay, next is Riemann sum approximations. I think you guys should have already gone through this in Calculus 1. But just as a reminder, what is the Riemann sum calculations? It's us actually doing these rectangles. So we do a rectangle, we calculate the area of one rectangle, add it to the area of another rectangle, add it to the area of another rectangle to get a good approximation. We won't do the integral, but we will calculate the area of specific rectangles to approximate it well. So how are we going to do that for this one? We're going to use something called the midpoint rule. So what does the midpoint rule? The midpoint rule means, in this context, what the midpoint rule means, using four sub-intervals. I'm going to use four, or not really sub-interval, but a sub-rectangle. The midpoint rule means whatever rectangles you draw, you using the center of the rectangle. The center of the rectangle is the point you want to use. So in this case, it's -1 to 1 and -1 to 1. So what are your rectangles? Your rectangles are your sub-rectangle. I'm just going to say R1 is xy such that -1 x 0, -1 y 0, right? And that's the only one I'm going to write in set builder notation, because I don't want to write in set builder notation anymore. So it will look something like this: rectangle 1, rectangle 2, rectangle 3, rectangle 4, right? So those are your rectangles, and they have width of 1 by, or your squares basically, and they have width of 1 by 1 for each rectangle. So you're going to try to use the midpoint of each rectangle. So what coordinates are you going to use? You're going to use 0.5, 0.5, 0.5, negative 0.5, negative 0.5, negative 0.5, negative 0.5, 0.5. Those are your 4 coordinates that you're going to use. And you will realize that each coordinate is going to give you the same answer, because negative or positive, if it's squared, it will give you a positive result. So what will you end up with? You end up with 1 minus 0.5 squared minus 0.5 squared. So what is this? This is 1 minus 0.5 squared is 0.25. 1 minus 0.5 squared is 1 minus 0.25 minus 0.25. So that's 0.5. Right? That's the height. That's the f of xy. So f of x1, y1, and x2, y2, and x3, y3, and x4, y4, they're all 0.5. So what is the base area? The base area, we've already established our rectangles. Maybe I should have that picture back up again. But the width and the length are both 1 with 1 long. So we'd have 0.5. So the volume of rectangle 1 is equal to 0.5 times 1, which is 0.5. And then we end up getting... Okay, let me move this down a little bit because this is annoying. There you go. And then what we end up getting is, since all 4 rectangles give you the same result, and all 4 f's give you the same result, the volume is equal to 0.5 times 4, which is 2. Now, if you're confused by this, we're not really going to do this too much because I don't think it's important. I think it's more important to know how to integrate, which is what we're going to do right now. So this is the representation of how we are summing all of the rectangles, all of the rectangular prisms up to give you the area of the curve, or the area, not the area, the volume under the surface. So the limit as m approaches infinity of the limit as n approaches infinity of the sum from I equals 1 to m, the sum from j equals 1 to n. So how is this going to work? You're going to do x1, y1. You're going to do x1, y1 first. Then you're going to do x2, y2, x3, y3, x4, y4, x5, y5 until you get to x1, y, or x... No, I'm sorry. x1, y1, x1, y2, x1, y3, x1 by 4, x1 by y5 until you get to x1, yn. Then you start on the next x. x2, y1, x2, y2, x2, y3, x2, y4, x2, y5. Then the next until x2, yn, and then the next x, x3, all the way until you get to xn, yn. And you're going to sum up all of those f's, and you're going to sum up all of those delta x's and all of those delta y's. That's how you get a double integral. So what do we do with double integrals? How do we perform them systematically? We have to turn the double integral into something called an iterated integral. So it has to be an iterated integral. What does iterated mean? Iterated means you do it again. So in this case, you do it twice. So how is it going to work? Well, if we look at our formula right here, we can see that, or we can deduce that volume is f of xi yj times delta x delta y, and we'd sum all of that, right? Or that's a really bad sum. So we'd sum all of the f of xi yj delta x delta y. This is your height, and this is your base area. So volume is height times base area. When we take it down into infinitesimally, what is your base area? Your base area, when delta x is small enough and delta y is small enough, is dx dy. Or dy dx. And we will and the fact that you could change those two variables for rectangles, only for rectangles. In fact, this is so important, I'm going to have another page for it. It's called Fubini's theorem. What does Fubini's theorem say? Fubini's theorem says if R is all of the points x, y, such that A is less than or equal to x is less than or equal to b, and c is less than or equal to x is or y is less than or equal to d, then the double integral of r f of x, y, dA is equal, and r is continuous, right? But you should assume that this is already continuous. F of x, y, dA is equal to, well, actually, yeah, I'll just put that right here, right now. And f of x, y is continuous. Then f of the double integral in the region R of f of x, y, dA is equal to the integral from a to b of the integral from c to d of f of x, y, dy dx. And that is also equal to the integral from c to d of the integral from a to b of f of x, y, dx dy. So how do you read this? You read it from the inside out. That's why it's called iterated. You read it from the inside out. It's like PEMDAS except with integrals. In the inside you do first, then you do the outside. And it works both ways. If you do C and D first, you will get, and then you do B and A, you will get the exact same result as if you do A and B first, then you do C and D. It's like partial derivatives with the Clairaut's theorem, where f of xy is equal to f of yx if the function's continuous and differentiable. But in this case, it only needs to be continuous. Then f of x, the double integral of f of xy dA is equal to these two where the bounds are switched. These two double integrals where the bounds are switched. So yeah, I already basically said what I was going to say in this slide. So we have to turn this into a double integral to evaluate. So how will we turn into a double integral? Well, it's the integral of 1 minus x squared minus y squared. Now this is -1 to 1 and -1 to 1. So it's not very nice. There will be situations where it's a little bit nicer, it's a little bit better to do it one way than another. But in this case, we will just do it the way that we're supposed to do it. I'm going to use dy dx for now. So dy dx, and then we have -1 to 1, -1 to 1. They're both the same, so I don't really have to care about the integral. So what will we do? We will do this. We will do this integral first. The dy integral, the y integral. Alright, let me write it better. So what's this? Well, how do you integrate? How do you integrate this? It's the same as partial derivatives. You just integrate the variable that is b that like you have to integrate, and then the other one will be kept constant. So how does that work? Well, it becomes 1. It becomes, so what's the integral of 1 dy is y. What's the integral of x squared dy? Now, since x squared is treated as a constant, we have to add in an extra y. So it's like integrating 5, right? You add in 5, you have 5y. So you're integrating x squared. X squared's a constant, x squared y. Minus y cubed over 3. And you take this from what? From y equals -1 to y equals 1. You do not take it from x equal -1 and x equal 1. You do not plug in -1 and 1 for any letter you see. That is wrong. and that will lose you a lot of points in your class. So do not do that. So that will give you the integral from -1 to 1 of what? Of 1 minus x squared minus 1/3 minus -1 plus x squared plus 1/3, which is just happens to be double. So that will give you 2/3 minus x squared plus 2/3 minus x squared, which is equal to -1 to 1 of 4/3 minus 2x squared dx. So let me shrink the thing. Oh my gosh, that's messy. Okay, I'm going to shrink the thing, and let's do the single variable integrals. Now it's very easy. Now it's very easy. So this is equal to what? This is equal to 4/3 x minus 2/3 x to the third power, evaluated from -1 to 1, which is 4/3 minus 2/3 minus, open, minus 4/3 plus 2/3, which is what? That's 4/3. That's your answer. So it's 4/3. 4/3 is pretty close to 2, right? 4/3, it should be pretty close to 2. Not quite. 4/3 is not quite close to 2. However, we will be able to see that as we get closer and closer approximations, or as we get better and better approximations, we will be able to do better and better, or get better and better, especially if you take like scores like courses like computational math or something. You will have to write some of these codes out, and you will see that you will get better and better approximations as you write or lower the number of intervals. And we actually only took 2 intervals from each side, so 4 intervals, 4 rectangles total. So it's not going to be very accurate, but if you do take it closer and closer, it will be more and more accurate. All right, let's do 2 more examples, or 3 more, because we have this now. So let's check if this is actually 0. So what will we do? Let's do the x first this time. So integral of the integral. I need to write smaller integrals. I also need to stop writing them so bad. 1 minus 2y. So which one do we want to do first? We want to do... I said we'll do x first, but in fact it's a better decision to do y first in this case, because there's a 0, and zeros will make things very nice most of the time. So x first will be -1 to 1, and then 0 to 1. This integral is easier than the integral that we did last time. Even though all the stuff in the inside is in terms of y, do not reduce it down to 0, because it's a constant. Remember, it's integrating, not differentiating. So the integral of 0 to 1 of y minus y squared, evaluated from -1 to 1 of dy. And I'm actually going to make it even more clearer. Y equals -1 to... Oh, I'm sorry. I just made the mistake. X minus 2xy, evaluated from -1 to 1 of dy. And this is x equal -1, x equal 1. So what will you end up getting? You will end up getting 1 minus 2y minus... So 1 minus 2y minus what? Minus -1 plus 2y. So what is that? That is 0 to 1 of 2 minus 4y dy. Now we take the integral of this. You will get 2y minus 2y squared, evaluated from 0 to 1 which is 2 minus 2 minus 0 minus 0, which is 0. And yes, we did calculate it correct. Our intuition, or my intuition, maybe yours, was correct. So the volume is 0. Let's do another problem. We're going to talk about this notation in a second. Actually, we're going to talk about it now. So what does this notation mean? And I'm going to tell you one other thing as well, which is pretty interesting to find out. But we're going to do that both ways. So this notation means the interval, right? It's just intervals, basically. So this is a rectangle, R for rectangle. And this is the x, like the x span of the rectangle, the x length. This is the y span of the rectangle. So if we're saying this, what we're basically saying is the x's are from 0 to pi over 2, and the y's are from negative pi over 3 to pi over 3. So the rectangle's like this, right? So the y's, all the y's are negative pi over 3 to pi over 3, and all the x's are 0 to pi over 2. That's basically it. It's not that hard to understand. So we can just do this like we do it normally. We will do the y first this time. Or actually, no, we'll do the x first. And the reason is there's a 0. That's why. How will a 0 make it easier? I will show you. Sine x cosine y dx dy. Which is what? This is equal to the integral of from negative 3 pi over 3, negative pi over 3 to pi over 3 of, since we're integrating x first, we have negative cosine x cosine y. And you can actually just take cosine y out of the integral. That would work as well. And then x is equal to 0. X is equal to pi over 2. Dy. Alright, so what would this give you? This would give you negative pi over 3 to pi over 3. Cosine of pi over 2 is what? Cosine of pi over 2 is 0. Cosine of 0 is what? Is 1. So what you end up getting is just positive cosine y dy. And then this is equal to sine y from negative pi over 3 to pi over 3, which is equal to sine pi over 3 minus negative sine pi over 3. Sine of pi over 3 is what? Sine of pi over 3 is root 3 over 2 minus negative sine of negative pi over 3, negative root 3 over 2. So it's root 3. That should be the right answer. Now, how could we do this differently? How could we have done this differently? We could have done this differently by another theorem. But I don't like saying that it's a theorem. It's not really a theorem. It's just a really simple or it's a really useful insight. Not very simple, but it's basically if f of xy can be written as f of xy is equal to g of x times h of y, which means that they are separable. So we just have x stuff multiplied by y stuff, x function multiplied by y function. For example, this right here, sine of x, is just x, an x function, multiplied by cosine of y, a y function. Then the double integral, or with a region R, right? With a region R. Oh my gosh, it's so annoying. This is so annoying. With a region R, or capital R, capital R. There you go. R of a, b. Yeah, I could have written this down, but I don't want to. AB cross CD, then the double integral of R f of xy dA is equal to the integral from a to b of g of x times the integral, or dx, I'm sorry, times the integral from c to d of h of y dy. So you can literally just separate both integrals. It's very useful. It only works if R is a rectangle. It only works if R is like this, right? So that means a rectangle. Clear interval with numbers on A to B, and clear interval with numbers on C to D, where A, B, C, and D are all constants, not variables. Very important. Only works if it is a rectangle. The region's a rectangle. It doesn't work if it's not. All right, final question. So for this question, you would actually have to strategize a little bit. You can use integration by parts, or you can use a better way to solve this. You have to see, you have to kind of see the problem. Let's see if you can see the problem. We have y cosine of xy right here. If you take the derivative of the inside, or do u sub, u is equal to xy. When you do u sub x, you get y, right? U sub x will get you y. So what do you think we should do first? Should we do dx dy or dy dx? I say we should do dx dy first. Because if you take the derivative of the inside with respect to x, you will get y. And why is this so nice? This is so nice because it's simply just going to be sine of xy from 1 to 2. Why is it sine of xy from 1 to 2? How can you do it that quickly? Because if you take the derivative of sine of xy with respect to x, you will get cosine of xy times the derivative of the inside. Derivative of xy with respect to x is y. So you'll get y cosine of xy. You have to find it's a u substitution or a reverse chain rule predicament. Cosine of xy, the derivative inside with respect to x is y. You see a y out here. If this was an x out here, we'd do the y stuff first, because the derivative of the inside with respect to y is x. So we're doing the x stuff just because it's nicer for us. So what will this give us? No dx. 0 to pi and dy. So what's this going to give us? It's going to give us 0 to pi of sine of 2y minus sine of y dy. Now we can integrate this easily. I hope if you guys remember your integration, then it will be very easy. If you guys don't, then it won't be so easy. Minus 1/2 cosine 2y plus cosine of y. Evaluated from 0 to pi, which is equal to cosine of 2 pi is what? Cosine of 2 pi is 1, so it's just minus 1/2, plus cosine of pi is negative 1, minus cosine of 0 is 1, so negative minus 1/2, and then cosine of 0 is 1. So you will get minus 2. And that's the end of today's lesson. I will see you next time for double integrals over stranger regions.